Good day, stat students. So today we're going to talk about section 2.5 part 1, and so section 2.5 is very long, and so I'm going to separate it into two different lectures. This is lecture number 1 for section 2.5. So today we're going to go over numerical summaries of quantitative variables, and we're going to start with measures of center. Where is the center of the data located? So I'm sure you've heard these before, is that we have the mean, which is just an average, the median, and the mode. And so all of these measure the center of the data. It's just that they measure it differently. And so when do you want to use these? Well, it depends on your data set. Okay, and we'll go through that. So let's say that we have a variable called ages, and it'll be the number of years, how old a college student is, and we'll call that big X. Okay, and let's say that we take a look at the first 5 students, and there's their ages. Okay, and since we called ages big X, little x will be the actual values for the data. And so x sub 1 would be 18, x sub 2 would be 21, and we'd doing that so that we could go ahead and utilize formulas in order to calculate, say, the mean. Okay? Alright, so let's say that we have a different variable. We'll call it minutes it takes 4th graders to complete a math assignment. And so we have 10 observations here. Most of the observations are between 1 minute and 6 minutes, but then we had a student who really struggled with it. It took 63 minutes. Okay, so we clearly have an outlier in our data. So we'll note that and see how that's going to affect things. Okay, so let's say that we took a look at the mean or the average, and so maybe you haven't read formulas before and seen formulas, but I'm sure we all know how to calculate an average or a mean. That we would go ahead and add up all the values of the variable and then divide by the number of observations that we had. And so this is our simplest looking formula, and so we're going to see this type of notation as we go through the semester. So we're going to have to get used to reading formulas. So the first thing is, what is that first symbol there? Well, that first symbol is a capital sigma, and it means to sum all the same things together. Okay, we got a bunch of the same type of things, and we want to add them all together. Okay, and so what do we want to add all together here? We want to add all the x's. Okay, so thus we're going to put the summation of x in little sub I, meaning I stands for all those different possibilities, 1 through 10 here. Okay, so we call that the summation sign, and it just means to sum something, okay, of the same thing. Here, all the x's. N is the sample size. Okay, how many people or things were sampled? How many people or things did we sample? 10. Okay, and so that means the mean or the average would have been 91 divided by 10 and turned out to be 9.1 minutes. Okay, now a lesson here is that the units would be the same as the units of x. That's 1. And 2, if you happen to calculate a mean that turned out to be that has a decimal in it, leave it. Don't round this to 9. Okay, certainly don't round to 10. Okay, don't round it at all. All right. Maybe you've heard, when I was growing up, I used to hear that the average household in the United States had 2.5 kids. Okay, so notice number of children per household is discrete: 0, 1, 2, 3. It's a discrete variable. All right, but the average turned out to be 2.5. We didn't round it to 2 or 3. We left it as 2.5. Okay, so averages can be decimals. Leave them. All right. All right. So the average turned out to be 9.1. Now, if you took a look at the first 9 observations here, 1 through the 6 down here, would you have expected the average to turn out to be 9.1 with just one more observation? Probably not. Okay, so 63 is clearly an outlier. And what did the outlier do? It really affected the mean here, right? It pulled on the mean. It pulled the mean in its direction. Okay, that's what outliers do. It pulls the mean in their direction. Okay, so let's just note this. Okay, and we'll see how this comes into play later on. So now this is the first example of specific statistics and parameters. And so we have two different means that we have to distinguish here. We have a population mean. Okay, so if we took a mean for the entire population, okay, that would be a parameter. Why is it a parameter? Because it's a measurement coming from a population. Okay, and we have to understand that there's symbols for each one of these. Please go memorize these symbols. Okay, it will benefit you greatly. All right, so the first symbol that we have here is mu. Anytime you see the Greek letter mu, okay, we're talking about a population mean in statistics. Well, we also have a sample mean, so it's a mean that's coming from a sample. That would be a statistic. It's a measurement from a sample. The symbol that we use here is x bar, so an x with a bar over the top of it. Okay. Yes, we sat up all night one night and said, hey, let's call this x bar, right? Nah, we're not very creative bunch statisticians, sorry. But anyways, anytime you see a Greek letter in statistics, I guarantee you that we're talking about a parameter, okay? And pretty much, there's one exception later on in the semester, but pretty much anytime you see a standard letter such as X or a standard letter with a symbol to it, probably talking about a statistic, okay? There is one exception, okay? There's a reason for it. We'll talk about that later, but pretty much Greek letters, parameters. Standard letters with maybe a notation to it, like a hat over the top of it, or a line, or just a standard letter, pretty much is going to be a statistic with one exception. Okay? Mu, x bar. Please memorize those. It's to your benefit. Okay. Later on in the semester, we will use x bar then to help us to understand where mu is located. Remember, we use statistics to help us to understand what? Parameters. Okay? Okay, let's move on. The median. The median separates a ranked or ordered data set into two equal parts based upon the number of observations. Alright, so what do I mean by ranked or ordered? Well, you probably understand that this already, that what we're talking about is that we're going to, based upon the values, we're going to put the data in order from smallest to largest. We're going to rank them. We're going to order them. Okay, so here is our data set again, but this is not ranked or ordered, is it? Okay, this is the raw data. Okay, so we can't use the way it looks right now, the data. Okay, we can't use the data how it looks right now to figure out the median. What are we going to have to do? We're going to have to rank or order the data set. So here, I've ranked it. I've ordered it. Okay. Now, how are we going to calculate the median? Well, first things first, rank the data set, order the data set. And then there's two rules. The first rule says if the sample size n is odd, the median is the middle value in a ranked data set. So if n is odd, it's easy. Go find the middle observation in the ranked data set. You got your median. 2. If the sample size n is even, the median is the average of the two middle observations in a ranked data set. So we got to do a little math. Okay, but the math isn't hard. So in our data set, n was equal to 10, so it was even. So we will use rule number 2. Okay, rule number 2. Okay, let's go back to our data set. And so, true, there is a simple little formula that I could give you that tells you what observation to take a look at roughly. Okay, but if we don't need a formula, I'm not going to give you one. Okay, and this is just to give you an idea of what's going on. Okay, so if I had to go find the median based upon this data right here, what I would do is I would just cross out the 1 with the 63, the smallest with the largest, and just keep on going. 1 with the 6, 1 with the 6, 1 with the 5, and what are we left with? 3 and 4, right? And so the values of 3 and 4 are the two middle. Those are the two middle observations. Okay, and so what are we going to do? We're going to average those two numbers, and we get what? 3.5 minutes. Okay. So literally the median sits between the 3 and the 4, and notice you would have 5 observations before the median. So you would have 1 through 3, you have 5 observations there, and then you would have 4 through 63, you have 5 observations there. Okay, and so it's separated the data set into two equal parts based upon the number of observations. Okay, so the median turned out to be 3.5. The mean turned out to be 9.1. So got a question for you. Which measure was better at describing where the center of the data is located? Now think about it. Let's go look back at our data. Which one do you think did a little bit better job? The mean or the median? I think in this situation, the median did a better job for this data. Now, I'm not saying that the median is the best measure of center for every scenario, but for this data, it was. Why was the median better than the mean? We got to figure that out, okay? And it's because the median is resistant to outliers. Resistant meaning it's the way we measure it, the outliers are not going to affect the median, okay? It's resistant to those outliers. Unfortunately, the mean isn't, okay? So there's a better rule of thumb that you need to understand. If the data contains extreme outlier or outliers, use the median over the mean. In all other situations, use the mean as a measure of center. So actually, for the most part, you're going to use the mean because most of the time you're not going to have extreme outliers in your data. Okay, so most of the time you are going to use the mean. But if you do have extreme outliers, median. Okay, let's move on. Let's say that we have a different data set. Here, the data set n is equal to 9. It's odd. Okay, that means the middle observation should be what? The median. So let's see. So I'm just going to cross out, right? I'll cross out the 0 with the 28 and 1 with the 27, so on and so forth. And what do we get down to? 15 is the middle observation. That's the median. So notice you got 4 observations before the median, from 0 to 12. Then from 20 to 28, you have 4 observations after the median. The median did its job. Separated the data set into 2 equal parts. Okay, what about the mode? The mode is the value in the data set that has the highest frequency. So taking a look at our data, now you can do this for just looking at raw data, but it's actually better to rank the data set so you can easily see this. So I've given you the ranked data set. Which one has the highest frequency? It would be what? 1, right? And so the mode would be 1. It has the highest frequency here. Okay. Now rarely is the mode used over the mean or the median. Okay, you need a real special situation. Okay, that special situation would be if you had discrete data where you had a bunch of values that were repeated. Let's say you had a data set that had a bunch of 1s, 2s, 3s, and 4s, and that's it. Okay, there might be a lot of worth then to use the mode in that situation as a measure of center. Okay, and just said which one was repeated the most. Okay, that's about the only time that you would use the mode over those other 2. Now graphically, can you sort of detect the mode? You can kind of get a feel for where the mode is located based upon some graphs. So let's say that we were taking a look at this bell-shaped curve. Okay, where do you think the mode would be located? Well, where's the spot where we have the highest frequency? Well, that would be right smack dab in the center of the graph, right? So let's see here. Here's the highest frequency. We would just drop a line right down. Where would that line take us to? Looks like 100. Okay, and so 100 would be the mode, at least right around there. I don't want to get into specifics why it may or may not, but probably right around 100 would be the mode. Okay. Now, this is considered a graph in data that is unimodal. Why? Because presumably, since there's just one hump, there's just one mode. Uni meaning just one. Okay, so this would be unimodal. Well, this would also be unimodal, this type of graph. Okay, so there's really just one hump to it. Okay, and I would say that the mode would probably be around right around 10 or so. Okay, so you don't have 2 distinct humps to this. You just basically have one, and then it kind of trails off to the right. Okay, this would also be considered unimodal. All right, how about the influence of shape on the mean and the median? So we talked about our different shapes. So we have bell-shaped symmetrical, right? How does that influence where the mean and median are going to be? Well, let's say that here is our bell-shaped curve, okay? Can you imagine where the mean and median would be located? And how close in value are they going to be? Well, first of all, for real data, okay, not theoretical data, but not for some theoretical distribution of data, but for real data, the mean and the median will be close to another. That's why I put the approximate sign here. They're approximately equal to one another, okay? And where they're going to be located is smack dab right in the center, okay? So for real data, they're going to be really, really close to one another and should be very much in the center of the graph, okay? If you have bell-shaped symmetrical data, okay? What about if the data is skewed right? So here's our skewed right distribution. Well, remember we have these outliers out here, 200 and about 230 and 300. What do those outliers do to the mean? It pulls on the mean, right? So we got to keep that in consideration. So the median is going to be located just probably to the right of the mode, okay? And that's why I put the median where I did. The mean is going to be pulled by those outliers, okay, down the number line, closer to them. And so the mean, you can see that the mean on the number line is a little bit further to the right, okay? In other words, the mean is going to be greater than the median for skewed right data. Skewed right data, mean is greater than the median. How about for skewed left? Here's a skewed left distribution, okay? Nope, I didn't mean for it to disappear. So what happens is that we have some values out here, may or may not be outliers. It's hard to tell from this, but those, since it's skewed left, the mean is going to be pulled that way, okay, a little bit. And so it's going to be pulled to the left a little bit, whereas the median is going to stay a little bit to the right, closer to the mode, okay? And so generally speaking, when you have skewed left data, the mean is less than the median. This is all leading to data analysis down the line, okay? All right, let's move on. That's the end of our section 2.5, part 1. So thank you for your time. So remember, we have a part 2 that I need you to take a look at. Thank you for your time.